Hello, AP Calculus students. We have jumped over Chapter 5.3 and all the way into 5.4.1, which I believe is the only part of 5.4, if I'm thinking correctly. Yeah. We're almost done with Chapter 5. We're going to keep pressing forward. We've hit, I think, the downward slope at this point. We know all the major formulas that we need to know for this class. From here, it's going to be a lot of application problems and a lot of other just practice-y things, getting you ready for that AP test in May. However, 5.4.1 deals with a pretty important and really, frankly, easy concept. So we'll be doing all the problems today for the homework. And let's just get into it. 5.141 and 5.142 both use the exact same graph that's shown right here. So we're going to use that. What we got is the graph of f prime. It's the derivative of some function f of x, which we're never going to know. It's composed, the f prime graph here is composed of straight lines and a semicircle. We're going to determine the values of x for which f has a local minimum, maximum, and points of inflection over the interval from -3 to +3. So for this, we're going to take a look at that graph, and we're really going to tell where it's changing from positive to negative or from negative to positive. Because we kind of know from this that a minimum happens when f prime of x goes from decreasing to increasing, so negative to positive. A max is going to happen when f prime of x goes from positive to negative, or in other words, increasing to decreasing. Now, a shortcut version of this is the idea that we're looking for when f prime of x equals 0. But we've learned in the past that that's not necessarily enough, because just because f prime of x equals 0 doesn't necessarily mean that it's changing sign there. A good example would be -1, where it's not changing from, it is 0 there, but it's not changing from positive to negative, so there is not a maximum there. As far as the other thing we got to find is, let's see, maximum and points of inflection. Points of inflection happen when f double prime of x changes sign. We don't necessarily need to differentiate between whether it's going from positive to negative or negative to positive. All we care about is that it changes sign. That's going to cause a point of inflection. Now, f double prime of x changing signs means that f prime of x switches from increasing to decreasing. Since f double prime is the derivative of f prime, so if f prime is increasing, f double prime is positive. If f prime is decreasing, then f double prime is negative. So we'll have to consider that too. So these are actually relatively easy to find. The point x equals 1 and the point x equals 2.5, I believe, are the only possible maximums and minimums. Those are the only 2 points that I see where this graph changes from positive to negative. So if I'm looking at my answers here, or at least our descriptions here, changing from positive to negative, that happens when x equals 1. You can see over here on x equals 1, you can see the graph is positive before and it's negative afterwards. So it's a local maximum at x equals 1. And then here at about 2.5, I think, we see the graph change from negative to positive, which means the original f of x goes from decreasing to increasing, and so there's going to be a minimum at x equals 2.5, like that. As far as points of inflection go, we're looking for places where this graph switches from increasing to decreasing. I see that happening here at x equals -1. I see that happening here at x equals 0. And I see it happening again at x equals, it looks like 1.5 or so. Those are the 3 places that I see the graph changing from decreasing to increasing. So x equals -1, x equals 0, and x equals about 1.5, I think, are reasonable answers for that question. So those are your solutions for where it goes from increasing to decreasing, decreasing to increasing. When the f prime changes from negative to positive, positive to negative, and also for where the second derivative will change or change sign also. So, all right, let's take a look at 142, which is going to take the same graph. This time they're going to bring in the idea that f of x, f of t actually, is equal to the integral from 0 to t of f prime, which is true. if you take the integral, that is going to be that's what the original function is. You can integrate this to find the original function. Well, kind of, in theory, because you need the whole plus c situation. Of course, they do give us an initial condition. They give us that f of 0 is equal to 2. And at y is equal to f prime of x is shown in the graph from 5.141. We're here to calculate the following values. So let's start with f of 1. I'm going to do problem A off to the side a little bit here because I think we're going to need some room for it. F of 1, if you look at the situation they've given us, it's this integral. It's the integral from 0 to 1 of f prime of x dx, which is actually really easy to find because it's just going to be the area under the curve from 0 to 1. And that's relatively simple to get just by using geometry, because now we're just talking about the area of this little semicircle there. Or, sorry, quarter circle. So that's going to equal, let's see for a minute here. The integral from 0 to 1 of f prime of x, that's going to be 1/4 of pi times 1 squared, or in other words, pi over 4. Now it seems like that might be the answer. However, we have to remember that f of 0 is actually equal to 2. So at 0, you actually already had a value of 2 going on. So we're going to add on to that the integral we just found. So the answer is actually 2 plus pi over 4, and that's what we're looking for the final answer. I'll put sparkles around that one to help differentiate it from the pi over 4 next to it. There you go. It's the initial condition plus pi over 4. Pi over 4 would be the change, but we need the change plus where it was to begin with. That's kind of what's going on there. Question B, f prime of 1 is stupid easy to get because all we're doing is looking at the graph and figuring out what the y value is there. That's just 0. That is literally the point on f prime, 1, 0. So that's just 0. F of negative 3 is, well, you know what we should also do is knock out D right now because it's asking the same thing. What's f prime of negative 2? Looks like about 1 to me. That was good. Okay, we'll knock those two out right away. This one was 2 plus pi over 4. Question C is going to have a lot of the same stuff going on that question A had. We're talking about f of negative 3, which is now 2. I guess, when I was writing this original problem, I should have put the 2 plus in front. It's 2 plus the integral from 0 to negative 3 of f prime of x dx. That's kind of what we're looking for there. Remember, 2 is kind of the initial position where it was. Now, you might also notice that this integral is backwards. So let's write it as 2 minus the integral from negative 3 to 0 of f prime of x dx, like that. Now, if we look up at this graph for a minute and we think about the area under the curve from negative 3 to 0, and we're subtracting now, so the actual positive thing, it's actually not too tough to get. The area of this triangle here is just going to be 1/2 times base times height, or 1/2 times 2 times 2, which is just going to be 2. And this area we kind of already know to be pi over 4 because it's got to be the same as that area right there because they're basically equal to each other. So it's going to be 2 plus pi over 4. So we're going to have, for this equation, we're going to have 2 minus, in parentheses, 2 plus pi over 4. And the 2's cancel out, and we're left with negative pi over 4 for our final answer, which is pretty groovy. Question D we already asked, and then answered, rather. And question E, f double prime of 2. This is asking us what the derivative of f of 2 is. Now, that's actually relatively easy to answer. At 2, you're looking at that point right there. Just don't forget what derivatives are. They are just the measurement of slope. So this is literally asking you, hey, what's the slope of this purple line right there? And I think it's pretty reasonable to suss out. That's about, I don't know, man. I'm going to guess it's 1, because this looks like about 1.5 to me and 1.5 here. So I'm going to guess it's about 1. I think it's a ratio of 1.5 over 1.5, which is 1. Just asking us what the slope is at that point, and since it's a straight line, it's the same slope the whole time through. 143. I can tell you this is going to be nice for you because this is probably the last time that we'll do an example kind of like these limit problems, because we're about to learn how to do L'Hopital's rule, which makes pretty much all limit problems a thing of the past if you remember how to use it. For question A, I don't like question A. I'm going to throw out question A. I'm not going to require you to do question A because I know what's going to happen here at the top. I have to Google it myself. but it's got a difference of cubes at the top, and I don't always remember what this formula is. I know it's x minus 2 on top, because it's x minus 2 on bottom also. I don't remember what the inside part here. I think it's x squared. Man, difference of cubes. Is it plus or minus 2ab? It's like plus 2x plus 2, I think. No, 4. Yeah. I think that's how it works out. I can't remember how difference of cubes works, but you would factor the top, and then you would just plug in 2 at the bottom. If you plug in 2 to this, let's see if I'm right. This would be 4 plus 4 plus 4, which is 12. I think that's correct. Oh, yeah. Hey, that's right. Cool. You guys don't need to worry about A. B, though, is completely within your realm of understanding, especially if you're... Actually, you know what? Oh, man. You know what? The more I look at this question, I was hoping for some basic limit problems, but these are not fun. I don't like B at all. B is Hannah's method. What we are meant to see right now is that the function is secant of 3x. So I'm not going to assign this question in class. So if you're watching this video, I apologize. You can skip ahead, but I'm going to do these problems anyway. This is not too tough to find the derivative of, because whenever you see limit as h approaches 0 with a fraction with an h on the bottom, this is a formal definition of derivative problem. So really, this is just asking you what the derivative of some function is, but in kind of a weird backdoor way. You're supposed to pick out from here that the original function is the secant of 3 times x. You see x plus h and x minus h in both of these things. So secant of 3x. The derivative of this, the derivative of secant, is secant times the tangent. And we're leaving the original inside part intact. We would then have to multiply by 3, which is the derivative of the inside part. It's a weird chain rule problem, but the chain rule says now we have to take the derivative of that inside part, which is 3. And so the final full complete answer is 3 secant 3x tangent 3x. That's that. C and D are a little more reasonable. This is asking you, in this question, this is asking us what the cotangent of pi over 4 is. Or I guess let's see, what's the derivative? Cotangent, let's see if I think about this correctly. The original function I think we're meant to see here is the cotangent of x. And we're looking specifically what's happening when x is equal to pi over 4. Because I see pi over 4 plus h in there. So that's your x plus h. And also, I'm just going to confirm in my head really quick, the cotangent of pi over 4 is 1, which it is. Not important for us. So we're looking for f prime of pi over 4 is really what's happening here. The derivative of cotangent is negative cosecant squared of x. So really, negative cosecant squared of pi over 4. And, man, that sucks. This is 1 over the square root of 2 over 2 squared. Yikes. I hate this problem. I hate it so much. It's going to end up being 1 over 1/2. Yeah. Yeah, 1 over 1/2, because it'll be 2 over 4, and then that's 2. I don't like that answer. That's dumb. I mean, it's just trig. And then this one is kind of the same thing. They're asking for us to recognize that this is the original function, f of x, is the tangent of 5x. And that we're looking for f prime of pi, in this case, which would be secant squared of 5 pi times 5. Because of the chain rule, we need that times 5 out there. You know. Let's see, 5 pi is... This is going to be 1. Because secant is 1 over cosine, and the cosine of multiples of pi is either 1 or negative 1. So it's going to go, pi is negative 1, 2 pi's. This is going to be negative 5, I think, when we're all done with it. Yeah. Oh, no, positive 5. Positive 5 because it's squared. It's positive 5. Okay, this is silly. Okay, next question. What do all the limits above have in common? Okay. All right, I withdraw my recommendation on this problem. Oh, no, what happened? Whoa, I just draw a big line. Now I gotta find it again. Shoot. Oh. How's everybody doing watching this video? I hope you guys are having a good time. Look at that big vertical line. It's gonna connect those two spaces that I just made. 0.2.5, 5.3.1. Oh boy, this might take a while, guys. I don't know what happened, but my tablet seems to have pooped his pants a little bit. I'm just going to keep scrolling and see if I can find anything over here. Oh, okay, that's good news. Well, we found something. Okay, that's better news. Keep showing me stuff. Keep going backwards. Oh, here we go. Okay, good. Oh, we're back in business. Okay, 144. Perfect. Okay. Hey, determine the coordinates of all the relative extrema and points of inflection for that function there. Now, you could take the derivative, because really what we're going to do here, when you're asked a question like this, what needs to be screaming out at you is, when is f prime of x equal to 0? When is f double prime of x equal to 0? Now, normally, you could take the derivative of this using the product rule. I would not recommend that. This is a relatively easy expansion to do, so we're going to expand it first, then we're going to take the derivative, and then we're going to take the second derivative, and we're going to do all that analysis. So let's deal with our original function first, f of x equals. We've got x squared plus 1 here, times the expansion of x plus 1 squared, which is going to be x squared plus 2x plus 1. That's our first step. We're going to expand that out. And now we're going to need to multiply all this together. We're going to have an x to the third. We're going to have a plus 2x. Is that x to the fourth? I guess it's x to the fourth power. Plus a 2x to the third plus an x squared minus an x squared minus a 2x minus a 1. So this is all going to be x to the fourth power plus 2x to the third minus 2x minus 1, which is going to make the rest of the work in this problem relatively easy to do. Let's start with the derivative, f prime of x. It's going to be 4x to the third plus 6x squared minus 2. And that is that. Whew, that is not going to be a fun one. I'm wondering if this is going to have nice answers to it or not. It looks like it does have nice answers, so let's see. How can I solve that? Fourth and third. Well, I suppose we'll just graph it and figure out from there. Sorry, got me thinking there for a minute. F double prime of x is going to be 12x squared plus 12x, which is kind of cool, the way that shakes out. That's going to be pretty easy to find x equals 0 on. Well, we'll deal with that in just a moment here. Okay, so as far as relative minimums and relative maximums, let's take a look at the first derivative. And honestly, for a graph like that, I don't see a nice, easy way to factor it, and it's next to the third power, so I'm going to graph it and see where it equals 0. Oh, my calculator hasn't been turned on in a week. Fun. Okay, so we're looking at 4x to the third power plus 6x squared minus 2. And then we're going to graph that on a good old standard window and see what comes up. This is the graph of the derivative. So we're looking for when this changes sign. And I only see one place where it's changing sign. It looks like a relatively innocuous 1/2. I'm just going to confirm that by using the calculate mode to find the 0. This is a spot where Decimos really shines. Oh, it is. It's at 0.5. So at x equals 0.5, based on what I'm looking at the graph here, I see the graph changing from negative to positive there. So that means that this is going to be a minimum because this graph changes from negative to positive. That means that the original graph goes from decreasing to increasing. So I'm going to write down that f prime of x equals 0 at x equals 1/2, where it changes from negative to positive. Therefore, there is going to be a minimum at the point 1/2, comma, Here's where I need to go to the calculator really quick and plug in 1/2 to the original function, which I'm going to do in its original form. 1/2 squared plus 1, that's the first chunk. I'm going to put a parentheses in front of that, all two. Times 1/2 plus 1 squared. I think that should do it. And it's going to be about 45/16. Ugh. Oh, did I put a negative 1/2 in there? No, it's positive 1/2. Did I get that right? Oh, it's -1. Okay. Okay. I'm just double checking that really quick. Yeah. You guys at home watching this? Mr. Ford, you're an idiot. -27/16. That's more what I expected. I make these videos with an answer key off the other monitor, so I know if I'm doing it right. That's the only minimum or maximum that I see. It looks like there's another 0 at -1, but it does not cross the axis there, so I'm not going to worry about it. As far as the second derivative goes, when does this equal 0? It's actually relatively easy to figure out. I mean, first of all, you can factor 12x out of everything. So it's 12x times x plus 1. And this means your two zeros are going to happen at x equals 0 and x equals -1. These are potential spots for where the points of inflection are going to happen. I'm just going to graph and confirm that they actually do change sign there at 0 and -1. And bam, bam, they do. So cool. Those are both your points of inflection at those points. I guess the actual points would be coordinates I can find by plugging this into the original function. Actually, really easy to do here, because the original function, which was x squared minus 1 times x plus 1 squared, if you plug in 0, you just get -1 times 1, which is -1. And if you plug in -1, you get 0 right there. And so you get 0 right there. Those are your 2 points. There you go. Points of inflection. Cool. Okay, that question I knew was going to take a little bit of time. So this is going to be a longer one. Already at 22 minutes, but we're almost to the end here. 145, write the equation of a line tangent to y equals cotangent of 2x at x equals pi over 3. Here is some legitimate trig for you, things you should be aware of, at least how to do. If you don't feel completely fluent in the math yet, it's okay, but you'll get there. You can do this. This is no different than our normal write the equation of a line problems. Let's start by figuring out what the point is that this is actually at. Let's figure out what cotangent of 2 times pi over 3 is, or 2 pi over 3. I wrote that kind of weird. It's 2 pi over 3. So we're really just figuring out what the y coordinate that matches this x coordinate is. That would be the cotangent of 2 pi over 3. I suppose we could use a unit circle for this. That is, let's see, I got to think about this for a minute here. Cotangent is cosine over sine, and at 2 pi over 3, the cosine is -1/2, and the sine is the square root of 3 over 2. If you divide those out, the 1/2s, I'm going to work my way through this pretty slow. I'm going to run into my work for the previous problem, though. Actually, let's move down here. What's going to happen is the 1/2s actually cancel out, and you're left with -1 over the square root of 3. That's the way I like to think about that, is you're actually factoring out a 1/2. You have 1/2 times -1, and 1/2 times the square root of 3. And so the 1/2s actually cancel out. And then, of course, if you rationalize this denominator, which nobody ever needs to do, but, actually, let's not do that. I like this answer. Rationalizing the denominator is not a thing anybody cares about. So the point is pi over 3, comma, -1 over square root of 3. That's going to be the coordinates of the point we're looking at. What we need now is the slope of this line. We can do that by finding the derivative, which we're going to need some room for. So I'm going to move down here into this space. Here's our original function, cotangent of 2x. And for the derivative, we're going to need to take the y prime of this. The derivative of cotangent is negative cosecant squared of the inside. And of course, we need to multiply that by the derivative of the inside because of the chain rule. So our final derivative here is y prime equals -2 times cosecant squared of 2x. And again, x in this problem is pi over 3. So this is going to get a little bulky with some fraction work in a minute, but it's nothing too seriously complicated. I like to think about this as 1 over the sine squared. of 2 pi over 3. Again, plugging in the x for 2 pi over 3 there. So I'm going to leave that negative 2 off to the side for a minute. I know that the sine of 2 pi over 3 is the square root of 3 over 2. So this is the square root of 3 over 2 squared. So that is going to be, I'm going to put that negative 2 on top of this fraction now. And on the bottom, I would have 3 over 4, because if I square both the square root of 3 and 2, you get 3/4. And if you flip that fraction and multiply, it becomes negative 8 over 3. That is the slope of that fraction, of that line. So, going back over here, we know that the point we're going to go through is the point pi over 3 comma negative 1 over square root of 3. We know the slope is now negative 8/3, negative 8/3. And so now it's no big deal to just put this into a point slope form and walk away. It's going to look stupid, but that will be the answer. I'm actually going to do that off here to the side. Point slope form would be this. It'd be y plus 1 over the square root of 3 equals the slope of negative 8/3 times, in parentheses, x minus pi over 3. And that, my friends, is the answer that I'm going to walk away from, because it is in point slope form. If you wanted to be fun, you could subtract that 1 over square root of 3 over. No. Walk away from it. You're good. 146, we got some multiple choice questions here. Let f be the function given by f of x equals the absolute value of x. Which of the following statements is true? Well, if you think about that graph in your head right now, you've seen it a million times. It comes down like this and goes up like that. So, is it continuous at x equals 0? Yes. Is it differentiable? A hard no. That sharp corner means it's not differentiable. Absolute minimum at x equals 0? Also true. So, 1 and 3. Love us some multiple choice questions. We're going to be seeing these more and more as we move into chapter 6 and beyond. And then 147. A function f is continuous over 2, 8, and has values that are given at the table at right. So, using subintervals 2 to 5, 5 to 7, 7 to 8, what's the trapezoidal approximation of the integral from 2 to 8? Now, I don't think we're going to look at B, but we at least do A. A does require that you kind of remember how trapezoids work, though. You're basically going to find the area of 3 trapezoids. The nice thing is the trapezoid area formula is pretty easy to work with. What you're going to do is you're going to add together the two bases, 10 plus 30, and you're going to multiply by the height, which is the difference between these two numbers, 3, 2, and 1. Like that. There's your first trapezoid. The second one is going to be 1/2 times 30 plus 40. A little overlap because 30 is shared with the previous one. This time the difference is 2. And the third one is 1/2 times 40 plus 20 times 1. Right there. Again, you get overlap with the every other trapezoid that you see there. Let me get this calculator cam out of the way. So, this is a lot of head math here. This would be a fair question for no calculator, so we'll do it without a calculator. Let's see. In this one, this is 1/2 times 40 times 3. This is 1/2 times... Actually, the 1/2 and the 2 cancel out in this one, so this is just 70. And this is going to be 1/2 times 60 times 1. So this is going to be 20 times 3, so that's 60 plus 70 plus 30. That's going to be 160 for your final answer. The units, though, I don't think there's any unit there. That's it. Simple. So that one's actually not too terrible. Over which subinterval is the average slope a minimum? That's a good question here. Average slope. Well, you could find the average slopes, I suppose. That might be a way to do it. Yeah, let's try that. The average slopes. So for 2 and 5, it would be 30 minus 10 over 3, which is 20 over 3. For 5 and 7, it would be 40 minus 30 over 2, which is 10 over 2. And then from 7 to 8, it goes negative. 20 minus 40 over 1, which is negative 20, which is by far the minimum, so it's 3. That's not too terrible there. So there you go. Hey, keep it up. What can I say except still continuing to be positive to you guys. I know it's winter. I know we're burnt out. I know we just had a 6-day weekend. We're pushing and pushing and pushing to the end. You guys are awesome and worth it. Keep it up, please. Keep up the great attitude, and I will see you in the next video.